Thank you all for coming to my talk, and thanks to the organizers for organizing this nice program. So someone mentioned to me during the lunch that I'm the only non-Italian speaker for today. But, well, I'm based in Ireland, and if you squint a little bit, then the Irish flag looks a little bit like the Italian flag, so maybe that's good enough for now. So I'll be talking about work I've been doing in the last few years with my group in Trinity College, which are my students Chiara Paletta and Anton Pribetok and Paul, well, he's not a student anymore, who is here in the audience, gave it up earlier, and with Boris Poska and Anna Rotoro, who will be in the program in a few weeks. And the central question that we were looking at is a question that's pretty sort of central to this program, is what are the solutions for the Yang-Baxter equation, and can we classify them and derive them? Basically, how do we find integrable models? So let's take a step back and think a bit what the definition of integrability is. That's something that we already discussed a little bit last week in the program. And the usual definition, at least in quantum mechanics or classically, is that you have a sufficiently large number of commuting conserved charges. But in field theory, 1 + 1 dimensional field theory, you usually use a slightly different definition. You look at scattering, and you want your scattering to be such that there is no particle production, and the scattering processes are factorized in two-body interactions in such a way that they satisfy the Yang-Baxter equation. So, of course, these two are sort of not really independent, and a very nice combining framework that relates these two sort of ideas comes from the algebraic beta ansatz formulated by the St. Petersburg school or Leningrad school back in the 70s and 80s, where you take a solution of the Yang-Baxter equation, written down here, and today I will be discussing the Yang-Baxter equation in the most general type. So I will not take R to be of different form. I will take it to be depend on the rapidities Ui and Uj separately. And then you use the solution of this, and you introduce a Lax operator, and then you use this solution to generate this tower of conserved charges for you. And then usually also use these operators that you built by using this R matrix to solve your system by making some sort of use of an beta ansatz type approach. Okay, so this Yang-Baxter equation in quantum mechanics and in quantum field theory is sort of the basic sort of hallmark of an integrable system. And it also appears because of this in various different contexts, ranging from quantum field theory to pure mathematics, when you study knot theory and quantum groups, to string theory and quantum circuits. So the project that we sort of set out to study is to see if we could find all solutions of the Yang-Baxter equation of a certain type, and maybe also the other way around. If someone hands me a Hamiltonian, for example, can I say if it's integrable, and if it's integrable, can I construct the solution of the Yang-Baxter equation that would correspond to it? And maybe even ask the question, are there integrable systems where you would have, say, a tower of charges, but not a solution of the Yang-Baxter equation that goes with this? Okay, so the plan for today is basically these two questions. First, I will describe for you a method that we devised to find solutions of the Yang-Baxter equation. And in the second part of the talk, I will turn the idea a little bit around, start from Hamiltonian and try to reconstruct the Yang-Baxter equation, the solution of the Yang-Baxter equation. And for this, I will focus on the long-range interactions. Okay, so how can we solve the Yang-Baxter equation? So historically, of course, many people have studied the Yang-Baxter equation. There are two sort of main ways that this has been handled. The first one is sort of the most famous one, where you assume that your system has some sort of big symmetry group that underlies it. So some quantum group like a Yangian or some temporary leap algebra. So if you assume this, then your life is very easy, because trying to find the R matrix that is compatible with one of these like symmetry algebras is very easy, because typically you only need to solve some set of linear equations. The downside of this approach is that, well, you only find models that have some manifest large symmetry group. So you might miss integrable models that have a symmetry group that's not manifestly realized, or not have a standard big symmetry group at all. There were also some attempts to try to find more direct approach. You look at the Yang-Baxter equation and you get a cubic set of coupled functional equations, and you try to solve that. That's obviously very hard to do. The plus side is that if you manage to do it, it would be complete, because you would find all the solutions of the equation. But of course, practically it's very hard to do, and it's very technical. So progress in this direction has been more limited, and mainly people were only able to solve it for R matrices of different form, and basically because of this approach. So the approach that we devised uses a little bit the properties that Gabor actually introduced yesterday already. So thank you for that. That will make my talk a little bit easier to give. And the starting point for our approach is not so the Yang-Baxter equation or the R matrix, but it goes back to the original definition of integrability. We use the tower of conserved charges as our starting point for integrability, and we try to sort of go back to an R matrix from that. So the upside will be that it's still complete, so we find all solutions of a certain type, and it's not as technical as the direct solution of the Yang-Baxter equation. We get a bunch of equations that you can actually are able to solve. The downside is that we have to restrict ourselves to regular R matrices, which basically means that we have to restrict to nearest neighbor interactions for now. And of course, there will still be some technical challenges that we'll have to deal with. Okay, so let me try to describe the main idea of our method. So let R mu nu be UV be a general solution of the Yang-Baxter equation. From this equation, if you follow the framework of Fadeev and company, we can associate a spin chain to this by interpreting the R matrix as a Lux operator. Then from this Lux operator, you can construct a monology matrix just by taking all your particles on the spin chain, take an auxiliary particle and scatter it through it basically. And a transfer matrix by tracing out the auxiliary particle. This will give you a set of operators on some spin chain V to the L with L states. Yes?
Do you need R for the permutation?
No. At this point, this is still general. This will work for any solution of the Yang-Baxter equation. The next step will depend on that property. Okay, and then the Yang-Baxter equation basically implies that TU commutes with TV. So the standard argument is then if I expand T in sort of charges Q2, Q3, and so on, then this relation means that I have that all the Q's will commute between themselves, and I have this tower of conserved charges that are all independent, that underlie my integrable spin chain. Okay, so starting from an R matrix, we can define a spin chain with a conserved set of charges. Okay, now I assume regularity, so I assume that R on U, U is the permutation operator. Yes.
What's the assumption about particle type here? How many particles are there?
Any number of particle types.
So
Yes. I'm not assuming. Yeah, I'm not assuming anything at this point at all. Okay, so okay, good. So if I assume that the R matrix is regular, so that means at the point U, U is reduced to the permutation operator, then I can show that the T at the special point theta, so R depends on U theta, you can see is the inhomogeneities of the spin chain, it just becomes a shift operator, because it basically becomes the product of a bunch of permutation operators. And then the next charge, Q2, which is the logarithmic derivative of t, becomes the nearest neighbor interaction, which is usually taken to be the Hamiltonian. Okay, so and then you can go on and take higher and higher logarithmic derivatives of your transfer matrix. You'll get more and more charges. But as was explained yesterday by Gabor, there's an alternative way to generate these conserved charges, which is the boost operator. So you can actually prove this rigorously from the Yang-Baxter equation that this exists, that there is an operator Q, B, that recursively generates your conserved charges. So if I commute B with Qi, I get something that's proportional to Qi plus 1. So in yesterday's talk, everything was of a different form. Gabor only showed the first part of the B. If you work with the general case, you have a derivative term in there as well. That's a derivative with respect to the inhomogeneities on the spin chain. Okay, so now you can observe that if we start from a Hamiltonian and you would compute Q3, so that would be the commutation of B with Q2. Q3 will depend on the Hamiltonian and its derivative, because of this derivative term. If you compute Q4, it will depend on the Hamiltonian and its first and second derivative with respect to theta. So in a sense, what you find is that the Hamiltonian is a fundamental building block of your tower of conserved charges. All the other charges are defined recursively in terms of the Hamiltonian and its derivatives. So this basically means that we had the idea to, rather than focus on the R matrix, take Hamiltonians as a starting point. So the idea was to take a Hamiltonian, h of theta, well, of some size. You can take any size you want. And we take the entries to be general functions of theta. So if it would come from an R matrix, we could take the boost and generate Q3. So that will depend on the Hamiltonian and its derivatives. And then we can just impose that Q2 and Q3 need to commute. Now Q3, as I said, depends on H and its derivative. So this will give you a set of coupled ordinary differential equations in the entries of the Hamiltonian, which you can try to solve. And often it can be hard work, but in lots of cases that we looked at, we could solve these sets of ODEs. So that gives you a set of potentially integrable Hamiltonians, right? Because demanding that Q2 with Q3 commute is a necessary condition for your system to be integrable. But then the question is, okay, so we have some Hamiltonians that could be integrable. How about Q2 with Q4, Q2 with Q5? Will they impose some additional constraints on your functions? Of course, it's impossible to check an infinite number of these commutation relations. So we'd have to do something else. So, and even that, if you would have these Qs, how would you get the R matrix out of it? So then comes step number 2. So we go back to the Yang-Baxter equation and we expand around a special point U1 equals to U2. So at leading order, it's trivial. But next to leading order, something nice happens. You get a commutator of product of R matrices with the Hamiltonian, which is something we know now because it has to be one of the potentially integrable Hamiltonians that we solved, is equal to derivatives of the R matrix, basically. So now what we get is, we get sort of in this limit of the Yang-Baxter equation, we get a differential equation that relates the Hamiltonian to the R matrix by some sort of overdetermined set of differential equations, because if you look here, there are more equations in principle than components of the R matrix. So it's a very restricted set of equations. And furthermore, we also know the boundary conditions of the R matrix because it has to be regular. So R of UU should be P, and the derivative of at UU should be the Hamiltonian, basically. Okay, so we have a very constrained set of differential equations with a sufficient number of boundary conditions. And indeed, in all the cases we looked at, plugging in the Hamiltonian, doing a lot of hard work and rewriting, we were able to get an R matrix out of that, a unique one for each Hamiltonian. And then, strictly speaking, you need to check the Yang-Baxter equation, because again, this equation, which looks like the Sutherland equation, is a special limit of the Yang-Baxter equation. So then you get an R matrix, you plug it in the Yang-Baxter equation, and you see whether or not it's satisfied. Okay, so that's sort of a whole step, a whole procedure, how to get from Hamiltonian to a tower of Kosev-Charkis to an R matrix and a solution of the Yang-Baxter equation. So, and like I said, this is unique, or sorry, complete, because we know that any R matrix automatically gives rise to a Hamiltonian that needs to satisfy all these properties. Okay, so we applied this to a bunch of different cases, which I'll discuss in a bit. But I would like to make some observations first that we found in our solutions. So the first observation that we made is that any Hamiltonian that was potentially integrable, so that solves Q2 with Q3 equals 0, actually turned out to be integrable. So Q2 with Q3 turns out to be a sufficient condition. And also solving this Sutherland type equation also turned out to be a sufficient condition. So it's something we thought a lot about and tried to prove or understand why this is the case. We never really managed to, but this seems to be a whole, because by now we've went through a very diverse set of different types of these equations, and Q2 with Q3 always seems to be enough. And also this solving this equation seems to be not just necessary, but actually a sufficient condition, which makes life a lot easier. I also mentioned that our classifications are in principle complete. So if you do this and you start from your Hamiltonian of a certain type, say 6 vertex, you go through our machinery, you will get all the Yang-Baxter equations, all solutions of the Yang-Baxter equation that have a Hamiltonian of this form. So one of the technical problems that I mentioned in the beginning to mention here as well. So we actually get a bunch of duplicate solutions in here as well, because solutions that are related, say, by basis transformations or reparametrizations, or just something as simple as parity transformation, or just a transposition, all these, of course, we will encounter in principle separate solutions. So in the final result, you sort of have to weed out or try to group what are the actual independent solutions, and not solutions, say, just related by a simple reparametrization. So that actually is not so easy. In some cases, we went down from 50 solutions all the way down to 5 independent ones. So that's actually one of the more technical steps that we had to do in this project. Okay, so what type of R matrices and solutions did we classify? So the first thing we looked at was 4x4 R matrices of difference form. So where the R matrix depends on the difference of the rapidities. And we were able to fully classify those. So we took all 16 elements to be non-zero and went through the machinery. And we found, of course, a bunch of all the known models like XXZ, XYZ, and so on, but also 6 new solutions of the Yang-Baxter equation. But those were a bit pathological in the sense that the Hamiltonians that correspond to these models are either non-emission or they are non-diagonalizable. So they have non-trivial Jordan blocks if you would try to diagonalize them. So then we went on and looked at 4x4 matrices of 8 vertex type, but we took the R matrix of non-difference form. There we found 2 new models, which turned out to be related to the ADS2 and ADS3 S matrices. But they were more general, so they were elliptic, and they depend on an additional parameter, which is the elliptic modulus. So in this way, we were able to classify all possible deformations of the scattering matrices of the ADS2 and ADS3 string sigma models. So this is a bit of a different approach than we usually take. Usually you would devise a sort of deformation of the string sigma model and see what happens on the S matrix. But in this way, we sort of found the S matrix that only integrable S matrices that you can possibly get, but we don't know the underlying sigma model that corresponds to it. So this in a sense.
So are these R matrices quasi-classical and fit into Beravin-Drinfeld classification, or?
That's a good question. So some of them do, some of them don't. So these for sure not, in the sense that their deformations ADS2 and ADS3, and so they depend on, so they correspond to super algebras basically. Okay. But the symmetry algebra that they seem to have is non-standard. So so I would say they do not fit in that classification.
I see. So for example, if you extend to super algebra, is it still beyond that? Or?
So we try to look at this for this elliptic deformation. It's basically not completely understood. At leading order, you get centrally extended PSU 1/1, or a Yangian thereof. But if you go to the second level of the Yangian, you get some K dependence in the commutation relations that we could not get rid of.
Oh, I see. So you mean the first order is the same, but the second order is different?
Yes, exactly.
But I see. That's surprising. Usually there's a kind of recursive structure, and then there's a...
Yes.
There's a uniqueness result, right?
Yeah.
Violation of that? That's fascinating.
Yes, no, exactly. And something that we don't fully understand.
Is this something to do with the fact that the symmetry algebra is not simple?
Probably.
Okay.
But basically it's something we don't understand. Many of these models actually sort of fall outside of the classification of Belavin-Drinfeld and the other symmetry algebras, because we don't assume any nice symmetry properties. So some of the R matrices, for example, don't reduce to something like the identity at some point, which makes it hard to identify, say, a Lie algebra that underlies them. So that's actually a very interesting point and something we want to look at, see what kind of quantum algebras these more general solutions correspond to. Okay, so yes, so in a sense, the S matrices here we found are sort of a solution in search of a problem in that sense. Okay, so we also did 9 by 9, 15 vertex, so where we satisfy the ice rule, which means it commutes with basically the diagonal part of SU3, so 3 U1s. We did some 16 by 16 Hubbard-like models. We found something that looks like the Hubbard model, but has different properties. For example, fermions can only move in pairs along the spin chain, and fermions, individual electrons are just stuck. Only when they're together they can move as a pair. So lots of these models have very, very weird properties. Another thing we looked at, so it was found a few years ago that some R matrices of integrable models can be thought of as Lindbladian, so super operators that describe quantum systems that are interacting with the environment. That was, I think, first done by Thomas Prosen, who was in the other program actually, where he showed that the Hubbard model corresponds to an XX spin chain that has a dephasing noise from the environment. So we were able to demand that our Hamiltonian or our R matrix is of a form of a Lindblad operator, and we were able to classify all integrable solutions or solutions in the Yang-Baxter equation that take this form. And we actually found a very nice new solution that has some non-trivial properties like a spin helix state and non-trivial equilibrium state. And there's a new paper coming out hopefully soon, where we actually find a new type of models that seem to have sort of a flag structure of a flag manifold, which seems to give a generalization of graded algebras. Actually, and yes, and if any of you has a good idea of what of a certain type of R matrix you would like to find with certain properties, please come over and have a chat. because we by now we're pretty experienced with finding these solutions, and like I said, it's complete. So once we go through our mechanism, we will find all integrable R matrices that have these properties. Okay, so let me now switch gear and go to the second part of the talk, which will be on long-range interactions. And for that, I want to inverse sort of reverse the logic a little bit. So if someone comes over to you and gives you a Hamiltonian, just a constant Hamiltonian, and says, is this Hamiltonian integrable? And can you find the R matrix that would generate, or is there an R matrix that would generate this Hamiltonian? So from our previous classification, it's not always so easy to check if this is the case and which R matrix corresponds to it. So first of all, there are all these identifications that we had to do, like basis transformations, reparameterizations, and that makes it life hard. And also, we found our Hamiltonians to be a function of the inhomogeneities. So this constant Hamiltonian could be one of our Hamiltonians evaluated 0.1 or 0.pi or something. So it's actually not so easy to just go through our list and see if this is possible. Okay, so so the question is, if someone gives you a Hamiltonian, can you find the Lax operator and an R matrix so that the fundamental commutation relations are satisfied and the R matrix satisfies the Yang-Baxter equation? And the Lax operator should satisfy the, again, I restrict to nearest neighbor. So the Lax operator should go like the permutation to lowest order, and first order should give the Hamiltonian. Okay, so now we can sort of repeat our procedure, but work with the Lax operator instead of the R matrix. So in the previous section, I took the R matrix as a special solution of the Lax operator. So let's now take a Lax operator here. So because of these boundary conditions, we will again find that T of 0 and define the transfer matrix in the usual way. You again find that T of 0 is the shift operator, and the first derivative is the Hamiltonian. And from this time, not the Yang-Baxter equation, but from the fundamental commutation relations that underlie the algebraic beta ansatz, you can again define a boost operator that acts on the Lax operator. It's a little bit more complicated, but it's okay. So, so now we can take a little bit more direct approach. So we know that our Lax operator to leading order is just a permutation operator, because that will give you the shift operator. To the next order, it will give the Hamiltonian, and then there will be some undetermined coefficients that will be determined by Q3 and so on. So you go and compute the Q3 by using this boost, and you find again that it now depends on the previous component of the Lax operator, which is the Hamiltonian, plus the first term in this expansion. So in a sense, the second derivative of the Lax operator. So all the new information at the thing Q3 is just restricted to a site that's only range 2. And then we do the same thing as we did before. We impose Q2 with Q3 equals 0. And if it has a solution, we find the next term in this expansion. Okay, now it's since everything is, and then if you would compute Q4, again, all new information is just in a two-site operator. So this actually makes it very easy to compute a lot of higher components in the Lax operator by just expanding the transfer matrix, basically. We were easily able to go to Q20. So that would actually give you the first 20 components in the expansion of the Lax operator. So if they exist, then you assume that it's integrable, but again, you can't compute an infinite amount. So at some point, you'll have to do some work, sit down and try to resum. And usually that's enough. So if you know something like 20 coefficients, so you're a bit clever with how you resum and commute things, that's usually enough to find L explicitly. And then the very nice thing is then if you go back to the fundamental commutation relations, which is took from RLL equals LLR, you see that it's simply linear in the R matrix. So if you know the L matrix, you can just solve a set of linear equations and you get your R matrix back out. So this is quite quite nice. So again, also here the L is not unique. For example, I could redefine my spectral parameter U with something like that goes like U to the third, because this will not affect the first two orders in my expansion. So there is some residual symmetry that you can use to make your life easy by making a nice choice. So that's one of the tricks that I mentioned that you should do if you try to resum this. And as a check, a sanity check that what we did was correct, we indeed checked that any 6-vertex model for general coefficients H1 until H6 is integrable. We found the R matrix and the Lax operator in this way by explicitly resumming everything. And what you get is indeed sort of a addressed version of the XXZ R matrix with some twists and basis transformations and so on. Okay, so this works. But most of these models are sort of known already in the sense that most interesting models have a known R matrix already. However, there is a set of models that Gabor mentioned yesterday that are generated by these perturbative long-range deformations. So all these deformations are defined on the level of the charges. So it's unclear if there is an R matrix and a Lax operator that corresponds to these integrable systems that would generate these charges. So that's the next question that we wanted to apply our formulas into, to understand if there is actually a solution to the Yang-Baxter equation that underlies these long-range deformations that are generated by the deformation equation. Okay, so the long-range deformations that we looked at are ones that are perturbatively formulated. So your Hamiltonian depends on the parameter lambda, and at leading order it's just a nearest neighbor Hamiltonian. At the next order you will have a next to nearest neighbor, and the order afterwards you'll have a next to nearest neighbor, and so on. So each order lambda, the interaction range of your operators grows. And in principle, these models are only integrable if you would take all orders in lambda into account. But for now, we will just truncate at a certain order in lambda. So we will say we will solve or see if there is a Yang-Baxter equation such that everything is satisfied up until some order in lambda, first order or second order or whatever. So basically, we want our two charges Qi and Qj to commute to some order of lambda r to the +1. And this is exactly, as was mentioned yesterday, the structure that you find for spin chains in ADS-CFT, where if you increase the loop order, the interaction range of your Hamiltonian increases by 1. Okay, so these type of deformations are generated by the deformation equation, which was derived by Bijzet, Bagheer, and Lubbert, which basically means that the derivative of Q with respect to lambda is given by some commutator. And then, as was shown yesterday, it's very easy to check that such a solution will map a commuting set of charges to a commuting set of charges. And in this way, it's compatible with integrability. And the solutions of these equations have been looked at for GLN and for 6-vertex type models, where it was actually found that all deformations of this type are generated by this deformation equation. So you can compute, for example, for the 6-vertex model, you can just assume that your Hamiltonian is of this form and check the solution space for which this is integrable, and then you can map it 1-to-1 to solutions of this deformation equation. So it seems that all solutions of this type are indeed generated by this deformation equation. Okay. And like I said, this deformation is completely defined on the level of the charges of the Hamiltonian, Q3, and so on. And it's completely unclear what it does on the R matrix. And it would be important to understand this. For example, if you want to use the power of the algebraic beta ansatz, you would need the Lax operator in the R matrix if you would want to compute some overlaps or some other things, for example, or understand the symmetries, say. Okay. So the approach to deal with this is based on work by Balázs by Poskay and Gombor, who had the following sort of smart idea. So if I have a spin chain here and I have a range 2 interaction and a range 3 interaction, what I can simply do is group my my sites into groups of 2, and then a range 3 interaction will be a nearest neighbor interaction, basically. In a sense, you make your spin chain smaller, or your sites bigger, and that decreases the interaction range. So you group sites together, and you're back to a nearest neighbor spin chain. And for that, we know how to deal with this, because this fits in our framework again. Okay, so they also had a very nice different observation, is that this will double the space for your Lax operator in your R matrix, and actually found that in this case the L operator, the Lax operator, factorizes into 2 different terms, and just considering one of these terms is actually enough to get your Hamiltonian and your charges out. So this means that I only have to double the auxiliary space, which makes things slightly less painful than they could be. But just going back to our procedure, it's very easy to just take the auxiliary space bigger and run through our whole machinery again and see what we get. So the first example we looked at was the SU2 sector in N equals 4 Suping Mills. And we went to 3 loops actually. So to leading order, it's just the Heisenberg spin chain, 1 minus permutation. And the next order contains something like P13. So that's the permutation between sites of 1, 3. So that's the next to nearest neighbor interaction. And then at G to the 4th, you have a range 4 interaction. Okay. So what we found after doing our machinery is that there is actually a very elegant Lax operator that corresponds to this Hamiltonian. So like I said, the Lax operator is now, the auxiliary space is space 1, 2 here, so that's bigger. It has a permutation part, 1 plus U times 1 minus P12, which is just the leading order Hamiltonian part. And then the next part is just the P13 here, times a quite simple rational function in U. Okay, so at 2 loops, this actually has a very, very elegant Lax operator. At 4 loops, it's not so nice anymore, in the sense that I couldn't fit it on 1 or 2 lines of the slides, but we have an explicit expression there as well. The R matrix is still big, and unfortunately, it's not very nice. So at order G to the 0, so if I look the lowest order, it does have a very nice interpretation. So there it just corresponds to a factorized scattering process of 2 particles with 2 particles, where one of the particles has rapidity U, the other one is 0, and the other one is V, the other one is 0, and you just scatter them, you get 4 R matrices, and you get this nice factorized product. So that's the leading order R. However, at the next order, corresponds to this term, this nice factorization goes away, and you will just have sort of an intertwined, entangled state with all of these particles. And we weren't really able to find a very nice way to write this or factorize this or interpret this. Unfortunately, that's still work in progress. And let me repeat here that both the Yang-Baxter equation and the finding relations are only valid up to order G squared for these solutions. So when you compute this, you will get orders G to the 4th and so on. And they will not satisfy the Yang-Baxter equation. So if you go to G to the 4th, you go 1 order further, you see that you have to take it non-zero if you have an order G squared. So that really shows you that this model is only integrable, fully integrable, if you take all the orders in the expansion into account. Just restricting to 1 or 2 orders will not give you an integrable model. It will only give you a perturbative integrable model. So in a sense, that's the soft symmetry breaking or the soft integrability breaking that you were talking about yesterday. Okay, so the other thing so like I said, it also works at G to the 4th, and in principle, we could go to any order. It becomes more complicated and more complicated because the size of the matrices grows and grows. So at some point, it will be computationally hard to do. But in practice, it's possible up to reasonable sizes. And I would also like to mention that integrability is not enough to say fix. You could say, maybe this Hamiltonian is uniquely fixed by some integrability and some other arguments, but that's actually not the case. So
does it mean that you can construct several integrable models?
Yes. So we found that at the order g to the fourth there were 2 free parameters. But if you impose something like parity, then you would go back to 1. But I'm pretty sure that if you would go 1 order higher, you would get more. And that makes sense if you think of the deformation equation of Nicholas. Basically, this. Let me go back. So this matrix X that you have can depend on lambda. So you can have a different deformation at each order in lambda. So there's a whole modular space of potential deformations that are possible. It's basically at each order you will have more and more possibilities of the long range deformations that you can have. And this special case of n equals 4 is sort of a special curve in that big modular space, but it's not singled out by things like integrability. So
do you have any intuition on what could be singled out?
No, not really.
These models, you can map them one-to-one into inhomogeneous models, and then there is some unitary transformation between the inhomogeneous Hamiltonian and this. And the coupling constant, so G4 will be some symmetric. The coefficients in front of this higher order, higher range interaction will be some symmetric sums of the inhomogeneities. So you have if the length of your spin chain is infinite, you have an infinite number of parameters that you can land on.
Yeah. So, but at least from the fact of integrability or having an R matrix, there's nothing that would single them out. So yes, you need some additional physical input from field theory or from string theory in order to fix what it is.
If the maximum permutation is enough, it's easy to fix from Feynman diagrams. Because that's not really a loop diagram. I mean, it is loop, but it's not really. It's
that's right, but I didn't write the g to the 4 term here, and it has more than just the maximum permutation. It also has some products of permutations that have maximum range, for example. So like a P12 times P34 and things like that.
Maybe this is also an easy Feynman diagram. Okay, yeah.
No, yes. I mean, I'm pretty sure that from Feynman diagrams you can fix lots of Fick's computation by looking at it. You should ask Charlotte because she computed. Yeah. Yes. But like I said, from the deformation equation, just from the point of view of integrability, lots of these coefficients can be chosen arbitrarily, but not all of them. So integrability, let's say, I think I have it on this slide, yes. So if you look at the 6 vertex model, in general, so not just SU2 spin chain, we classified in previous work all these long range deformations, and you can find that there are 6 nearest neighbor coefficients, terms h1 until h6, just in your 6 vertex Hamiltonian, and there are 5 possible long range deformations at the leading order. At the next order, there's something like 15. But all of these, actually, we were able to show have a Lax operator in an R matrix that corresponds to them. So we found the Lax operator in R matrix that depends on 6 plus 5 parameters at this order. How do you know? Oh,
Similarity and Transformations.
Well, basically, you just look at Q3, and they all multiply really different operators. So each of these 5 parameters, they multiply something like sigma z1, sigma z, or sigma plus, sigma z, sigma plus. They really multiply different operators that they don't see how you could map to each other with the normal similarity transformation or basis transformation. And like I said, they also correspond one-to-one to solutions of the deformation equation. And the axes that you use to generate these solutions are also completely independent and different. So one corresponds to a sort of a boost operator, the other one is a bilocal operator. So also the way you generate these from the deformation equation are completely different. So that's why we're pretty sure that they're independent. But this does seem to indicate that all solutions of the deformation equation actually have an R matrix and an X operator underlying them that would generate them. Okay, so let me wrap up then. So I showed you today, or explained our methods to find solutions and classify solutions of the Yang-Baxter equation. And we were able to apply to several different cases and find a bunch of new solutions of the Yang-Baxter equation. And then we discussed how to lift a constant Hamiltonian to an R matrix. And we applied that to spin chains that have these perturbative long-range interactions. And we were able to find Lax operators and R matrices for all of these spin chains. So, but there are lots of interesting open problems, and let me mention some here. So first of all, we would like to understand why just having Q2 with Q3 is actually a sufficient condition. So far, it's an experimental fact. Like I said, we tried very hard to prove this, but failed miserably. I've had 2 PhD students write thesis, and all of them had the idea maybe we could prove it in the thesis, but no luck. We would also understand, since this deformation equation corresponds one-to-one to these long-range deformations, there should be some way to let this act on the Lax operator in the R matrix, and understand on a more basic level what this equation does to your integrability structure. But that's also completely unclear. Tried a little bit, but unclear how to do it. It would be very nice to understand how does this actually work. Like I said, there are plenty other cases that we would like to study. Deformations of the Hubbard model, or if any of you has your favorite type of model that you would look at, we would be very happy to talk. So far I've done regular R matrices. It would be interesting to see if something is possible for non-regular R matrices. But there I don't really have too many ideas what to do. It would also be very interesting to do something for other proper long-range spin chains. So here, what we did was the perturbative long-range expansions, and your starting point is sort of a regular R matrix. It would be interesting to see if, for example, a Haldane-Chassis model or something could have an actual Lax operator in R matrix that would correspond to this. The other is maybe a bit more technical, but still think very nice, is that so far all the R matrices that we found, we could actually solve the differential equations in terms of known functions, elliptic functions, square roots of trigonometric functions. But some models that are, well, unpublished, or we sort of got stuck, we were able to write the differential equations, but not really able to solve them. And also Mathematica was not able to solve them. Of course, that doesn't mean that there is no solution. Maybe we were just not smart enough to write it in terms of fundamental functions. But it would be very interesting if an R matrix, say, exists for which the entries would only be defined in terms of some implicit solution of a differential equation, for example, with some properties. That would be quite interesting. We do have some R matrix that seems to be not, say, of rational, trigonometric, or elliptic type. We have an R matrix that depends on square roots of elliptic functions, and we haven't found a way to get rid of the square roots. So it's actually quite interesting. And like I said, we had plenty of properties of these new models, or we have plenty of new models, and it would be interesting to understand the properties, look at symmetry algebras, physical properties of these things. But we would have to decide which models are most interesting to look at first. And for long-range interactions, of course, if you want to apply to ADS-CFT, it would also be very important to understand, say, wrapping corrections, and see if you could write an R operator or a Lax operator for the full SU2 sector, for example, and understand how the integrable spin chain, or what the integrable spin chain actually is for the full SU2 sector, including wrapping and everything. And a little bit of progress has been made there by Gombor, who gave a talk about this in IGST. Yeah, and there are plenty of other things that I'd be interested in doing more for this. Okay, so thank you.
So thanks for the nice talk. Can you go back to your long-range two-loop OR matrix or lax operator, whichever?
Yes.
Yeah.
Lax operator, this one?
Yeah, this one. So I guess we know that the U-dependent part.
Yes.
So I guess the zeros of this thing correspond to where the transfer matrix is related to momentum in the usual sense,
Yes,
right?
yes.
Yeah, so is there any physical interpretation of the location of the poles that you have in the next order term?
Good question. I have no idea. So yes, no, that's a very good question, and I agree that's a very natural thing to look at. But yes, because the poles could depend on here, right? So our first idea was to see if we could sort of force Joukowsky variables into this, but we failed because the G to the fourth term, which I didn't write here, was not particularly nice. Let's put it that way. We weren't really able to make it into a nice form. But it doesn't mean it doesn't exist, because I strongly believe it should be possible to make sort of the poles here or write things with Joukowsky variables that you would expect, because they show up in the Bethe equations for SU2, right? So so yes, that's probably possible, but we don't understand how to do it yet.
Is it possible to do this for infinite dimensional system?
Maybe. So far we only did finite dimensional systems, so we could work with matrices. However, if you could say think of an SL2 spin chain and work with some differential operators, you might be able to generalize this to that case. We haven't tried. It's something that's on my long list of things to look at. So we haven't tried, but it might be possible, because things like the boost operator. So nothing here depends on the fact that things are finite dimensional. Just from a practical point of view, when we implement it in the computer, we work with finite dimensional systems and matrices. But the principle, things like the boost and everything should also work for infinite dimensional cases. So it should be possible to generalize this to that case, yeah. But of course, the equations that you get might be very complicated. So you don't know if you will be able to solve it, but in principle, you should be able to formulate this program for infinite dimensional systems as well, yeah.
Okay, about this Q2, Q3 problem.
Yes.
So if you, in field theory, if you just take a general Lagrangian, you know, you fix the first higher charge and fixes the interaction potential. And the point is that reminds me about this Sparks theorem, you know?
Yes,
that,
yes,
that yes. Yeah, you already thought about that. Then
yes,
I don't...
yes.
Okay.
No, yes, no.
So is that a really bad idea? Have you gone along this line and tried to find the explanation?
So yes, we thought about that, but we were never really able to make it work on the level, say, of spin chains and these commuting charges. So I do believe that there might be something along this lines that could work, but we were never really able to get it to work. But yes, I know that from field theory, something like this is not so surprising. But at least this, when we try to just introduce Q2 with Q3 and then try to prove that Q4 commutes with Q2 or Q5 or try to construct R, we always run into some functions that are only implicitly defined and that are like the charges basically, that are only these J's that you had yesterday, that are implicitly defined, and it's very hard to really say what you can do with those. So that's usually where we run into problems to actually prove things.
Okay, thank you for the nice talk. I have a question about, so when you are building this lax operator with a higher dimensional auxiliary space.
Yes.
So one of the main interests of having a lax operator is to be able to do better ansatz.
Yes.
So build the wave functions.
Yes. Yes.
Do you think it's possible to do it here?
I think so. It's one of the projects I'm working on now to see how we can do it. You would have to imply some sort of nesting procedure, because you're, for example, if you just look at that's range 3 part, you will get a 4x4 transfer matrix. So you would have 3 possible choices of creation operators. And it looks a bit like, say, the transfer matrix you would get for an SU4 spin, for an SU4 spin chain or for the Hubbard model, say. And there you can do this by doing sort of a nested procedure. And we are currently looking into if we can make this work for this model, basically. And the question is, I think it will work, but we don't know how yet.
Okay, so we were trying to deal with longer range interacting spin chains. So one way to do it, inspired by works of Vincent Pasquier, Denis Bernard, Haldane, was to hide the long, or to deal with the long range nature of the interaction by taking dynamical inhomogeneities and then freeze these degrees of freedom, block them. But that was not flexible enough to incorporate all this family of deformations that you can get by boost operators. So yeah, it would be nice to compare the two approaches and see how the two can be reconciliated.
Yeah, I completely agree, because also on by one of the papers by Gromov-Verviers, one of the tailoring, they create or construct the two-loop eigenfunctions using this theta morphism that also uses derivatives, and that was one of the motivations to understand, if you could understand from an algebraic beta ansatz point of view, how to get these eigenstates in the beta states. Yes.
So I wanted to ask you about the case in which you get this deformation of the ADS tree.
Yes.
So do you also see these quantum deformations, because there are like these regular 2 parameters, 3 parameters, and the last of these is still a bit mysterious, I guess.
Yes.
So can you see anything related to that?
So I believe we could deal with the quantum parameters, but although I forgot the exact details, I have to confess. But yeah, the Qs, I think we could incorporate them in there. But the elliptic parameter, that's the one that we don't understand how to put it in there.
Maybe we can have a chat.
Yeah.
I was wondering, I guess you can also do alternating spin chains just with more bookkeeping, or are there any principal?
So in principle, yes, you could also do them with a similar trick with do more bookkeeping. We are currently looking into what we can do there, basically. But yes, in principle, the same sort of tricks and techniques that work for these long range would in principle work for alternators.
No new challenges.
Maybe if you talk to Ellie, the new challenge is that you might have a dynamical Yang-Baxter equation, and of course what we assumed here was just the usual Yang-Baxter equation. So alternative spin chains that have a normal R matrix, in principle there should not be any new challenges. If you would have someone that has some dynamical R matrix, like an n=2 theories, then there are new challenges, basically.
Any other questions? I guess then we just thank Marius.